So this next lecture is on forces and free body diagrams. It's section 2.1 in your textbook. Now this is an important slide, and I'd recommend you copy down the what you see in green, the kind of chart that you see there. Basically, when we analyze motion, what you would have learned kinematics in grade 11, and kinematics essentially is your last two boxes. So you have A, and the relationship between A and V dt. So that's the relationship between acceleration, velocity, distance, and time. When we get into dynamics, we're interested in the causes of motion. So that's the forces, and that really is the F equals ma equation. So in order to kind of add that to the five equations that we got from Newtonian mechanics, we would use FBD, the free body diagram, to find out what the net force is. So that's our F net. And then use F equals ma to find our A. And then we can use our motion equations to find out what's missing, V, D, or T. And this goes the other way around. If we needed to find out what the net force is, and we had a combination of A, V, D, and T, we can use those to find out what our A is, and then we can use F equals ma to find out what our F net is. And if we're trying to find a specific force, we can use our drawing of the free body diagram to see which force is missing, and then find out what our missing force is from F net. Here's a sample problem. So it says an object with a mass of 15 kilograms rests on a frictionless horizontal plane, and it's acted upon by a horizontal force of 30 newtons. What will be its velocity after 10 seconds? So our first step here is to find the acceleration, because there's no way to find out there's no direct way to find force to velocity. So to find that acceleration, we use F net equals ma, and we know the force net is 30, and the object is 15 kilograms, so 30 divided by 15 gives us 2 meters per second squared for acceleration. To find the final velocity, we use the equation v2 equals v1 plus at, and we solve for that to be 20 meters per second. Another problem. So in this case, we have a car. We know its mass. We know it's moving at a constant speed. The driver applies the brakes, and the car stops after 25 seconds. So the applying the brakes is causing a negative acceleration or a deceleration. So to find that, we have enough information, knowing that V2 is 0, V1 is 30 meters per second, and our T is 25. We rearrange that equation and solve for A. We get minus 1.2 meters per second squared. And then from that, we can find out what our F equals ma, we can use F equals ma to find out what our F net is. And that would just simply be a multiplication between minus 1.2 times the 1,000 kilograms. We end up with negative 2,000 newtons forward. So negative because it's going back, and we have to round for our significant digits there as well. So in almost every instance of motion, more than one force is acting on an object. So to apply Newton's second law, you need to find the resultant force. So that's why we use a free body diagram. And we'll look into a sample about how to draw a free body diagram on the next slide. Here we have some children pulling a wagon. One child pulls a wagon forward on a rope tied to the front, while the other pushes on the wagon from behind. So we'll take a moment to draw the free body diagram of this, and it says that there's a hint there are 5 forces in total. So for free body diagrams, I prefer to use a box. You can use a dot or any other kind of something that's basically representing our object. In this case, it's the wagon. So this box is our wagon. We have a child pulling on this. So I will put this as Ft for the tension force in the rope. We have a child pushing this as well from this side, but we can draw that over here as well. That's FP for push, or FA for applied force. We'll also have a force of friction, FF. And we'll have the force of gravity, and then the force of the floor pushing up on the wagon is called the normal force. So this slide summarizes some common forces that you'll encounter, and of those we have gravity, the normal force, tension, friction, applied forces, and air resistance. So one type of friction is called static friction. It's the force that tends to prevent a stationary object from starting to move. So once the object is moving, we have kinetic friction. That's the force that acts against an object's motion in a direction opposite the direction of motion. For horizontal motion, the applied force, if the applied force has the same magnitude as the friction, the moving object will maintain uniform motion. So in other words, if the object is at rest, it will remain at rest. If it's in motion, it will be in motion. It'll have a constant velocity. So this next problem we're going to look at, it says we have a 0.17 kilogram hockey puck slides along the ice at 19 meters per second east when it hits a rough patch of ice that is 5.1 meters across. So we have a coefficient of kinetic friction, which is 0.47. And we're going to take a break to solve this. So for this hockey puck, we'll draw it as a box again. It has a mass of 0.17. So that means that we have an Fg going down of 0.17 times 9.8 newtons. We will have an Fn that is equal to our Fg. Now it's moving 19 meters per second to the east. We're going to take this as east. We don't draw the velocity vector on the free body diagram unless you're specifically asked to. But what we do draw is the frictional force that opposes that FF. So this is our free body diagram. Now if we're asked to calculate the friction, the kinetic friction acting on this, what we are going to do, that FF is equal to mu k times Fg, and our mu k is 0.47, our Fg is 0.17 times 9.8. So quickly calculate that. 0.47 times 0.17 times 9.8, and it works out to 0.78302. Now, while you're not being marked on significant digits for the first quiz and test, just to show you how to do that, looking back at the question, my lowest number of significant digits is 2. In fact, all of the given information has 2 significant digits. So I'm going to write this as 0.78 newtons, and the direction is west. That's my answer for the kinetic friction. The next slide asks you to solve for the acceleration. So I have my friction. My acceleration can be found using F equals ma, and my F net is that friction there. That makes this 0.78, and my mass is 0.17. My A is unknown. My A becomes 0.78 divided by divided by 0.17, I end up with 4.606, or 4.6 meters per second squared to the west. And the last thing they ask me in this question is to calculate the VF. So to find the VF, my VI is 19 meters per second to the east. My D is 5.1 meters. We know the acceleration from the previous. It was 4.6 meters per second squared to the west. You have to use the equation V2 squared, or VF squared, equals VI squared plus 2AD. And that becomes the square root of 19 squared plus 2, and I'm going to make this negative 4.6, and this is 5.1. That ends up being, I don't have my calculator here, just a second, 19 find the square root of that. So I end up with 17.72 meters per second, or 18 meters per second to the east. That's my final velocity. So, to determine the sum of all the forces acting on an object is straightforward if all the forces are linear or perpendicular, but quite often we have forces that are not that are at an angle. So we do that, like this example here. We have somebody pulling on a crate at an angle of 15 degrees. What we have to do is take our applied force and break it up into components. So we'll use sine and cosine to find that. Another situation would be this here: somebody pulling up on a sled, so they're on the surface is on an angle. Again, we would use the sine and cosine to find out the components of the force. So here's a person pulling on an angle. That same question again. Drawing the free body diagram, we have the Fn and Fg that are perpendicular, that are opposing each other in the same direction, or in opposite directions. We have the FF, which is perpendicular to the floor, but the FA is at an angle. So if we're to break that up, it would look like this. That FA, which was 115, would have to be multiplied by cosine of 15 to find the x, and sine of 15 to find the y. Seems like those are very low values. Let's see here. 115. Okay, well, those values might not be correct, but I assume they are. The concept is the same though. So basically what we're doing is we take the force, the FA, multiply it by sine of 15, or sine of the angle to find the component of the force in the y direction, and cosine of the angle to find out the component in the x direction. And lastly, because we can create, we know that we can use the free body diagram to find the net force. We can then use that to find the acceleration, and then use that to find an unknown like t. So I won't go through this problem. I'll let you try to solve it. Of this entire lecture, I'm just going to go all the way back to this. This is the most critical thing to know. The relationship between finding the free body diagram to F net to A, and then to VD or T. So make sure you know how to do that.